All right, this is the intro video for Calculus BC, section 3.3. We're going to be looking at increasing and decreasing functions here first, then we'll skip a little ways ahead and we'll talk about the first derivative test. Okay, so let's talk about increasing and decreasing first. Let's look at this little statement down here. If f is continuous and differentiable, and if f prime is positive for all x in a particular interval a to b, then f is increasing on that closed interval. So I'll just draw a quick graph here. This is going to be a graph of f of x. And so if f of x does something like this, it starts here and curves its way on up, maybe something like that, then if that's f of x, remembering that f prime is talking about the slope of f, then I think at every point along this particular interval, like whether we choose this point here or that point there, any of these points along here, we can say that f of x has a positive slope, so you could then say if f of x has a positive slope, f prime is positive. So that would be one way of looking at it if you see a graph of f, but let's look at it a little bit differently. You will often see things presented like this. Instead of having a graph of f in front of you, you might have a graph of f prime. So if you have a graph of f prime, and perhaps the graph of f prime looks something like this. Oops, let's try that again. Who knows, maybe something like that. This would not necessarily coordinate with the graph I drew earlier, but if this were a graph of f prime, you would look at this and say, well, for our interval from roughly right there over here to right here, for that entire interval, f prime is above the x-axis. Therefore, f prime is positive. Therefore, f is increasing. Like I said, this would be a more common way of seeing it presented. A quick way to say this, if f prime is positive, then f is increasing. And of course, we could have a case where f is decreasing. So hopefully this will make sense based on what we just talked about there. So if f is continuous and differentiable, and if f prime is negative for all the particular x values in an interval, then f is decreasing on that same interval. So again, let's look at it from this perspective. If I have a graph of f of x, let's say the graph of f of x starts here and it does this, then, again, remembering that f prime is simply describing the slope of f, I think it'd be fair to say that no matter which point we choose to focus on this particular interval, all those points in there, f of x has a negative slope, so you could say that f prime is negative, and we can see from the graph that f of x is decreasing. But like I mentioned on the other one, you will not see it often presented like that. You will often see one of these presented like this. Maybe we get a graph of f prime, and maybe our graph of f prime does something like this. Again, this wouldn't necessarily coordinate with the graph of f that I just drew, but maybe it does something like this. So if we were given a graph of f prime and asked, all right, what's going on with f? Is f increasing or decreasing? Really all we got to do is say, well, f prime is always below the x-axis, meaning that f prime is always negative. And if f prime is always negative, that means f always has a negative slope, which means f is decreasing. So sometimes people get confused about what they're looking at. They would look at this graph of f prime and forget that it's f prime, and they might look at this graph here and be like, well, hey, that graph is increasing. Of course, that's true, but that's a graph of f prime, and we're trying to describe the graph of f. The truth is, f prime is always negative, at least on this particular interval. Therefore, f would have to be decreasing on that interval. So again, a quick way to say this, if f prime is negative, then f is decreasing. So just a little note down here below, the converse of these statements isn't necessarily true. So in other words, you can't say if f is decreasing, then f prime is negative, or you also cannot say if f is increasing, then f prime is always positive. So maybe just something for you to think about tonight. Can you think of a counterexample? Like, can you think of why the converse is not necessarily true? We talk about that next time I see you. All right, we're going to skip ahead a little bit to the first derivative test. All right, this is a video continued here with the first derivative test. Let's remind ourselves a little bit about some key terms. Relative, also known as local extrema, are going to occur always at critical points, or critical numbers. And these are locations where the derivative is 0 or doesn't exist. The first derivative test basically is presented in 3 different scenarios. And let's take a look at the first one. So if c is a critical number, we've already proven that through whatever means we needed to, and f is continuous on the open interval, so that's the condition here for the first derivative test, c is within that interval, then f must be differentiable as well, except possibly at c. So those are kind of our conditions. Case number 1, if f prime goes from negative to positive at c, then f has a relative minimum at the point c comma f of c. So if we look at a graph of f of x, let's say that we have a minimum. Let's see here, a minimum could easily look something like that. So let's say we have a minimum right there at x equals 3. We can see here that the slope of f goes from negative to positive, therefore creating a relative minimum at that critical point. We could graph f prime and we could see the same sort of thing happening just from a different perspective. So when x is 3, we've got a horizontal tangent line. That means that f prime is 0. So that means that f prime would be right there. And then since f prime is measuring the slope of f, f prime would go from negative to positive. So of course this graph on the right, this is how we would often see these questions presented, where we get a graph of f prime and then we're asked, well, what does that mean for f? Does f have a relative min or max or neither? This wording up here in number 1 is kind of a basic framework for how you could justify your answer for a relative minimum. And as we'll work together in class a little bit to make sure that you're doing a good job with constructing your justifications and the wording for proving what you're trying to prove. Okay, let's take a look at the second situation. So in this situation, this says if f prime changes from positive to negative. So notice this is the exact opposite pattern of sign change for f prime. This is happening at our critical point. Then that would mean that f has a relative maximum at c comma f of c. So this could look something like this. You could have some curve that comes up here. Let me try that again. Some curve that comes up here and goes back down. You can see that right about here you've got a relative maximum. And so this would be a graph of f of x. And with that graph of f of x, maybe you can see that the slope of f goes from a positive value to a negative value. And so given a continuous function and a critical number right there, those conditions guarantee that you've got a relative maximum. So this is all happening at what, x equals 1, 2, 3, 4, 5 approximately. So if I were to graph f prime, then again I know that I got a horizontal tangent line right there at x equals 5. So 1, 2, 3, 4 looks like right about there. I would have a place where f prime is 0. And f prime is going from positive to negative, so something like that. I went a little bit too far with that line there, but I think you get the point. So again, this would be how it's presented over here. Typically, this would be the most likely situation that you would see, where you're given a graph of f prime and then asked, does f have a relative min, max, or maybe neither? All right, we got one more case to look at. Let's take a look at it on the next page. So in case number 1, we found that f prime went from negative to positive. That created a relative minimum for f. Case number 2, we found that f prime going from positive to negative creates a relative maximum for f. In case number 3, what if f prime doesn't even change signs at our critical number? What if f prime remains positive around c or remains negative around c? Then that means that f of c is neither relative min nor max, making it an inflection point of f of x. So a nice example of this, let's call this a graph of f of x, would be something like this, kind of the real basic cubic looking graph, like f of x equals x cubed. So in this situation, what we've got going on is we have, well, first of all, we've got a critical point right here. I did my best to draw that in there. Critical point right there at x equals 0. To the left of x equals 0, f prime is positive. And to the right of x equals 0, f prime is still positive. So in other words, f prime did not change signs. That means that we have neither a relative min nor max. And what we do have is an inflection point. The derivative, I'll just draw this right on top. We could graph the derivative of this, which would be f prime of x is equal to 3x squared. Of course, that would just be kind of a skinny, tall parabola, something like that. And you can see right here, f prime is 0, and that means that x equals 0 is a critical point of f. But f prime does not change signs. F prime actually remains positive on either side of x equals 0. Therefore, we have neither a relative min nor max. We have what's called an inflection point, which is just a bending in the graph. And we'll explore inflection points quite a bit coming up in the next section in your book. So just to further expand a little bit on inflection point, like I said, it's a bend in the graph. One way of defining an inflection point is a place where f prime changes from increasing to decreasing or decreasing to increasing. Depending on the situation, what's actually happening, either one of those would be a good description, a good justification of an inflection point. All right, we'll discuss this more when I see you next time.